I want to start with a question. Have you ever gone to sleep with a problem and woken up with the answer? I don't mean a vague sense that things might work out, but the actual answer arrived at cleanly, as if somebody had been working on it overnight and left the solution on your pillow. Have you ever had the right words for a difficult conversation appear while you were in the shower, 3 days after the conversation you actually had? Have you ever walked away from a coaching session feeling like not very much happened, and then a week later realized that something in that session had quietly rearranged how you think about something important? Most people explain these experiences the same way. The brain was working in the background. Most people mean that loosely as a comfortable mechanism for something they cannot quite explain. This week, a paper published in Nature gave that casual phrase a precise and rather startling scientific meaning. Researchers recorded the activity of individual brain cells in people who were completely unconscious under full general anesthesia. And we differentiate between non-conscious, which is the stuff that you're not aware of, and unconscious means you're gone. So it's not the basic hearing machinery. It's not the early sensory areas that process sound. It's the hippocampus, the deep structure at the heart of memory, meaning, and learning. And what they found was this. The hippocampus was not just hearing the sounds being played in the operating theater. It was understanding the meaning of words. It was predicting what word would come next. It was learning, getting better at detecting unexpected patterns without anyone directing it to. Nobody was at home, and the work was still getting done. Today, Cole and I want to explore what that means. Not just as a nerdy neuroscience finding, but as a reframing of how you think about your own brain, your own learning, and the value of those moments when you stop trying.
Welcome to Neuroscience Digest, powered by my BrainWise coach. I'm Bastian.
And I'm Phil Dixon.
And today we're looking at a brand new Nature paper that found the brain's memory and meaning-making center doing sophisticated work, understanding language, predicting, even learning, in people who were fully unconscious under anesthesia. We'll establish what the finding overturns, walk through what the researchers actually did, and then get practical about what it means for insight, for the time between coaching sessions, and for how you protect the conditions your brain needs to deliver its best work. As always, if this show helps you think differently about how your brain works, please leave us a 5-star rating and review wherever it is you get your podcasts. And comment, share, and subscribe on all our social platforms. You can find us everywhere at My BrainWise Coach. So before the research, let's establish the assumption it challenges. What did we think we knew about what the brain can do below conscious awareness?
The conventional picture, and the one I've been used to for a long while, has been a hierarchy of processing, with consciousness sitting at the top and authorizing the sophisticated work. The early stages of perception, detecting that a sound has occurred, processing its basic qualities, those were known to happen automatically below awareness. The brain doesn't need to be paying attention to know that a sound happened. That work is handled by the sensory machinery close to the brain's surface, the areas closest to the input. But the assumption was that the more meaningful, more sophisticated the processing involves understanding, predicting, connecting new information to what's already known, that required conscious engagement. The idea you needed to be present, attending, awake, and directed toward the information for the higher order work to happen.
There's already some evidence that this assumption was maybe too simple. Sleep research had shown that the brain consolidates memories during sleep. The experiences and learning of the day get processed and organized overnight without any conscious direction. The insight literature, the research on what produces these sudden aha moments that seem to arrive from nowhere, had established that they're often preceded by a period of not thinking about the problem, during which the brain appears to be doing something useful with it out of conscious view. And there were clinical observations that patients under anesthesia sometimes retained fragments of what was said during surgery in ways that were hard to explain if the brain had been entirely off. But these were pieces of a puzzle, not a coherent account. So what makes the new finding different in kind, not just degree?
Well, the difference is where the activity was found and what it was doing. The brain has a structure called the hippocampus, sitting deep inside, roughly behind your ears and below your temples. It's not a sensory area. It's not anywhere near the machinery that processes incoming sounds. It's the structure most central to memory formation, to learning, to the connection of new experience to existing meaning, to the construction of mental models of the outside world. It's anatomically distant from the sensory service. Information has to travel a relatively long way through many processing stages to reach it. And the assumption has always been that a structure that deep in the processing chain, that far from the sensory inputs, will be the first to go offline under anesthesia. The last place you would expect to find complex activity in an unconscious patient. And that's precisely where the researchers found it.
So tell us, what did the study actually do?
The team led by Sheth at Baylor College of Medicine was working with patients who were having a specific type of brain surgery. The detail is not important. And who had consented to have recordings made of their hippocampal activity during that procedure. The recordings were made with probes so fine that they could pick up the electrical signals from individual brain cells, individual neurons, the way a very sensitive microphone can isolate a single voice in a room. Once the patients were fully anaesthetized and completely unconscious, the researchers played them two types of sounds, sequences of sounds and recordings of natural speech.
The hippocampus was active.
Yeah, it was not just active, it was doing specific, sophisticated things. The first finding was with the tones. The researchers played a regular repeating tone, the same sound over and over, and then occasionally inserted a different tone into the sequence, an unexpected sound. Now, in a conscious, awake person, the brain reliably detects these unexpected intrusions. It's one of the most fundamental things brains do. Notice when something doesn't fit a pattern. The new finding was that the hippocampus was doing this detection even under full anesthesia. But wait, there's more. It was getting better at it over the course of the experiment. Over about 10 minutes, the hippocampus became more sensitive to the unexpected tones, more reliable at detecting the deviation. In other words, it was learning. Without any conscious direction, without anyone knowing what was happening, the learning was simply an emergent property of the hippocampal circuit that was running.
The language finding, which is the one that genuinely might stop people.
The language finding is the one that I found most remarkable. When I read it, that was like, oh my gosh. When the researchers played natural speech, actual sentences, the kind of language you hear in a conversation like this, the hippocampus was representing not just the sounds, but the meaning. The brain cells were responding differently to words with different meanings, to sentences with different grammatical structures. The hippocampus was processing the semantic content, what the words meant, not just the acoustic properties of the sounds. And then the most striking part, the hippocampus was predicting. The patterns of activity contained information about what word was likely to come next before that word arrived. The predictive processing that we've described throughout the BrainWise series as the brain's fundamental operation, the constant generation of predictions about what is coming, they were running in the hippocampus of an unconscious patient.
Nobody was home and the prediction engine was still running.
The prediction engine still runs. in the structure most responsible for connecting new experience to existing knowledge and memory, under full general anesthesia. The researchers' own conclusion, in their words, was that complex processing of sensory stimuli occurs in the hippocampus even in the unconscious state. Now, that's a careful, measured scientific statement, blah, 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 boring. What it means in plain English is that the brain's higher order processing does not require the conscious operator to function. The operator can be entirely absent. The processing continues.
I think we should name something before we move on, because it matters and it's easy to skip right past it. This has real implications for what patients hear during surgery.
It does, and it's worth naming clearly, even though it's not the main subject of this episode. If the hippocampus is processing the meaning of language and connecting it to existing knowledge during anesthesia, then get this, what is said in the operating theater during a procedure is not necessarily disappearing into the ether, into silence. The research does not tell us that patients are consciously aware of what they hear, or that they will remember it in any conventional sense. But it does suggest that the assumption that an anesthetized person is entirely beyond the reach of language may be just too simple. The clinical and ethical implications of that are significant, and they're being taken seriously by the researchers.
Now the connection to the everyday experience you opened with, because this is where the finding becomes genuinely useful rather than perhaps just remarkable. The shower moment, the insight that arrives when you're not trying, the answer that appears when you're doing something else, the solution that surfaces 3 days after the problem, has always been described loosely as the brain working in the background. What the anesthesia research does is show us the mechanism with unusual clarity, because anesthesia is the most extreme possible version of not trying. If the hippocampus keeps doing sophisticated language processing and predictive learning under full anesthesia, a state far more removed from conscious engagement than anything you experience in the shower, then the background processing that produces insight in ordinary life is not marginal. It's the hippocampus doing what it was designed to do without requiring your conscious attention to do it.
And we've mentioned it before, the default mode network, and it's directly relevant here. We've touched on that in earlier episodes, but it's worth making the connection explicit. The default mode network is a set of brain regions that become most active when you're not focused on an external task, when you're daydreaming, resting, letting your mind wander. For a long time, this network was assumed to be doing nothing particularly useful, idle processing, background noise. The research of the last 20 years has established that it's doing something of the most important cognitive work available: consolidating memories, making connections between disparate pieces of information, simulating future scenarios, integrating experience into the self model. The default mode network is most active precisely when you're not trying. And the hippocampus is a central node in that network. The shower moment is the default mode network delivering a result that it's been working on, sometimes for hours, sometimes for days, but below conscious awareness.
What does this mean practically for how people should think about their work? I'd start with what we might call non-productive time. The walk without a podcast, the shower, the drive without a phone call, the deliberate sit down with nothing to do. These are not wasted times. They're the conditions under which the hippocampus delivers its processed output to conscious awareness. The person who fills every gap with stimulation, who is always listening to something, reading something, responding to something, is preventing the delivery of the background processing. The insight is ready. There's nowhere for it to arrive. And the second piece is a reframing of the relationship between a coaching session and the work that happens afterward. When a session surfaces something important, a new way of saying a pattern, a question that hasn't been asked before, a connection between two things that seemed unrelated at the time, that insight doesn't do its most important work in the session. It does its most important work in the days after, while the hippocampus keeps processing it below awareness, connecting it to everything else the person knows. The coach who feels the most significant sessions are the ones whose effects only show up weeks later isn't imagining it. The hippocampus was working on it.
And that leads to the most practically actionable implication, which is how we design the space between sessions. If the hippocampus continues processing after a session, then the gap between sessions is not a void waiting to be filled with homework and action items. It's an active processing period. The most useful design of that gap is one that creates conditions for the hippocampus to deliver. Time without structured cognitive demands. Reflection practices that invite rather than force insight. And sufficient space between the prompts that the brain can do its associative work without being constantly redirected. The platform module that asks the user to return to a reflection 3 days after the session is not asking them to revisit old material. It's meeting them at the point where the hippocampus is most likely to have something ready to deliver.
Let's make the personal threat profile or PTP connection before we close, because the background processing this paper describes isn't uniform across profiles. The prediction driver is the most directly relevant. The hippocampus's core activity, as this paper describes and as decades of prior research established, is the construction and continuous updating of a model of the world. What has happened, what's likely to happen next, what fits the pattern, and what doesn't. That's exactly what the prediction driver monitors in conscious awareness, whether the model is reliable, whether the uncertainty is tolerable, and whether the prediction is holding. The person with a highly sensitive prediction driver has a hippocampus doing that monitoring with particular intensity, which means they may have a particularly active background processing system, more insight delivered during non-directed time, more vivid shower moments, but also more anxiety when the model is being disrupted and the hippocampus is working hard on something that it hasn't yet resolved.
And the participation driver connects to that same machinery. The hippocampus is also deeply involved in social and relational memory, the storage and retrieval of information about other people, about relational context, about the history of specific relationships. The participation driver's sensitivity to belonging and relational safety draws on this same hippocampal system. The person with a highly sensitive participation driver, who's also had a relational rupture, a conflict, a disconnection, a moment where their belonging felt threatened, may find the hippocampus continues processing that experience well beyond the point where conscious attention has moved on. The replay of the conversation in the small hours, the sudden reconstruction of what the other person's expression really meant. The hippocampus delivering its relational analysis at 3 a.m. is not dysfunction. It's the system doing what the new research confirms it does, working below awareness on the things that most matter to the person whose brain it is.
So you might be asking, what do we do with this practically? 3 things. First, create space for delivery. The background processing produces insight continuously. The question is whether there's a gap in your cognitive schedule for that insight to surface. Protect some genuinely unstructured time every day, not as a luxury, but as the condition under which the hippocampus can complete its work. Second, trust the delay. When the answer to a problem doesn't arrive during the concentrated effort of working on it, that's not failure. The hippocampus may need more time and more associative space. The answer is more likely to arrive during the walk than at the desk. And third, design the re-engagement. When an insight does arrive, in the shower, on the walk, in the gap between meetings, capture it immediately, because your conscious mind is receiving the output of a process that's been running for some time. That output is often fragile at the moment of delivery. Write it down before it dissolves back into the background. So, Phil, let's close out with the single most important thing.
This might sound a little difficult, but the brain you walk around with is larger than the part of it you're consciously directing. The conscious mind is the part that shows up at meetings, answers emails, and applies deliberate effort to define problems. The hippocampus is the part that works on everything else, the things that matter most, the connections that are hardest to force, the predictions that need time to be properly built. It was doing this before the new research was published. It was doing this while the patients in the study were unconscious on an operating table. It's doing it right now, with whatever you brought to this conversation. The shower moment is not a lucky accident. It's the hippocampus keeping its appointment. The only question is whether you leave the calendar clear enough for it to arrive.
The primary paper is by Katlowitz and colleagues, led by Sheth at Baylor College of Medicine, published in Nature in May 2026. The research highlight by Henrietta Howells appeared in Nature Neuroscience on June 8, 2026. Both references are in the show notes if it's of interest.
The hippocampus is listening. It was listening the whole time. The question is whether we are leaving enough silence to hear what it's found.
Thank you for spending time with us today, BrainWise friends. Stay curious, stay compassionate, and always stay
BrainWise.